Okay, so today we're going to go over this least squared problem and then example, and then we'll go over the Galerkin method using an example, and then we'll do a slightly more realistic example, which I'll go through the 3 different methods on the computer. So last time we were talking about the weighted residual method. So if we look at just the boundary, just the subdomain problem, essentially what we have is we have a residual and a weighting function. And so the residual is the function where we've substituted in a trial equation. So we substitute a trial equation in to a differential equation, and we get out some non-zero value, and that is the error, because the trial function is not exact. It doesn't give the exact answer. So it gives an error when we substitute the trial function into the problem, and so that gives us this residual. Then we have this weighting function, which can be different things. And so what I'm trying to do with this discussion is look at 3 different weighting functions and see how they work. So last time we talked about the collocation method, where the weighting function is chosen to be the delta function, and so for a 1D case, we would have the weighting function as function, say, of only x, and then this was the example problem where this d would be some differential term, for example, the second derivative of y with respect to x, and so this would be a residual. So if we chose the weighting function to be the delta function, then basically that means that the objective there would be to make the residual go to 0 at particular points in the problem region. So if the problem is this here, and we have a problem from 0 to 1, then we ensure that the boundary conditions are satisfied with our trial function, and then we'd also satisfy that we'd make sure the solution is has a residual of 0 at a number of points, and we chose 2 points to make the residual equal to 0 in order to try to determine the solution to the trial function, and we actually got the exact solution out. Again, this is just a simple example that we're going through, and then I'll give a more complicated one that shows the error more clearly between the different approaches. Okay, so that's the collocation, and then the second approach we looked at was the least squared method. And so the idea of the least squared method is to try to minimize the square of the residual. And so, but we need to, in order to minimize the square of a residual, we need to determine what the unknown terms are in the trial function. And so in order to find the unknowns, we have to take the derivative of this and find the minimum, because we want to minimize the error. So if you take the derivative of this with respect to the unknown coefficients in the trial function, then you'll get out this equation here where you've got this partial derivative. So then if you look at this equation here and compare it with this one for the 1D case, and then you can see that the weighting function will be the derivative of the residual. So that's the idea for this one, that we try to minimize this equation here where the weighting function is chosen to be the derivative of the residual. And so that's the idea. And now let's solve this same problem, this problem here, this first order problem, using this least squared method. So I'll just run over the approach and the whiteboard. Okay, so we had last time that for our problem, the residual is the same for each of the three different approaches. This is the residual. So for this problem that we talked about last time. So now, but we don't know what alpha 1 and alpha 2 are. So we're using three different approaches to find alpha 1 and alpha 2, basically. So the second approach is the least squared. So let's take the derivative of this residual. So evaluate so we're going to have d alpha, the derivative of our residual with respect to alpha 1, and so that's just going to be 2, and then the derivative of r with respect to alpha 2, that's going to be 6x. And so we have two problems to solve, two equations to solve, and two unknowns. So equation 1 would be this, where the derivative with respect to alpha 1, and then equation 2 would be the partial derivative with respect to alpha 2, and we set them both equal to 0. So then we can substitute the residual equations, a residual equation in to these two equations, and we get out 2 times 2 alpha 1 plus 6x alpha 2 minus x dx, and that has to be equal to 0. And so if we solve that, we get out 4 alpha 1 plus 6 alpha 2 minus 1. We can check that. And then we substitute in the second residual terms. And set it equal to 0, and then we get out 6 alpha 1 plus 12 alpha 2 minus 2 is equal to 0. So we have two equations and two unknowns, and so we can solve those. Solving for unknowns, we get out, surprise surprise, alpha 1 equals 0 and alpha 2 equals 1 over 6, which was the same answer we got for the collocation. So now, and you'll see that in the more practical example, the answers are different for each approach. So the Galerkin method involves choosing the weighting function to be the basis function. And so we'll see what that means. So for example, if the trial function is given by so we had this was the trial function that we were using for the two previous two previous examples, right? And last one we worked out that alpha 1 and alpha 2 was 0 and 1 over 6. Okay, so this is our trial function. So we can write this trial function as alpha 1 psi 1 plus alpha 2 psi 2. So we've got some function of x times an unknown, a second function of x times an unknown. So these functions here are quite special. So they're called often the basis function. So these are the basis functions. So Galerkin proposed, this is not obvious, Galerkin proposed that to choose the weighting function to be the basis functions. So that's not an obvious thing to do, but it turns out to be it's a very good way of minimizing the integral for the weighted residual approach. So let's just see how this works. So we have the residual and the weighting function, right, for our 2D, our 1D example. And so in this case, the weighting function has two parts. So we're saying that the weighting function for term I is going to be equal to the basis function for term I. Okay? So that's actually, if we look at this equation, that's actually the trial function, the derivative of the trial function with respect to alpha 1 would give the basis function for 1. Trial function, derivative of the trial function with respect to alpha 2 will give the basis function for term 2. So we can write that this is equal to the derivative of the trial function with respect to alpha I. So in this example then, we can write that W1x is equal to psi 1x, which is equal to x squared minus x. That's the first part, and then the second weighting function is W2 is equal to psi 2, and that's equal to x3 minus x. Okay? And so then from the last example, we worked out the residual equation for the case when we had n minus m equals 2 unknowns. So we've got two unknowns, alpha 1 and alpha 2, and we got out that the residual for our problem was 2 alpha 1 plus 6 alpha 2x minus x. So that hasn't changed. So again, the only thing we're changing in these three different approaches is the weighting function. So in this one, we're choosing the weighting function to equal the basis function. So then now our integral here that we set equal to 0 there's two equations. So we have we have wx times rx dx, right? That's in 1D. And so in this case, we have two weighting functions. So we have two unknowns. So we can write this out as integral from 0 to 1 times weighting function 1, which is x squared minus x, and then that's times the residual, 2 alpha 1 plus 6x alpha 2 minus x dx is equal to 0. And then second equation is the second weighting function times the residual, which is x to the 3 minus x times 2 alpha 1 plus 6x alpha 2 minus x dx equal to 0. And so we have to integrate this. So this is slightly more involved because it's got x to the 4 powers. So when you evaluate these two terms, and so this is, I could write this out as, just let me write this as psi 1 x times rx dx. That's what we're doing, and psi 2 x rx dx. So you could see, if you wanted to, you could have a trial function with 3 terms. There'd be then 3 basis functions, and then you'd have 3 equations and 3 unknowns. So you know, it would just be more time consuming to solve. So in this one we can solve these 2 integrals, and if you do that, evaluate integrals, then we find that alpha 1 is equal to 0 and alpha 2 is equal to 1 over 6. The same solution. So now you can check that if you want. So all 3 of these approaches give the exact answer. So then you might say, well, what's the point of this? Because they all give the exact answer. And the reason they all give the exact answer is because this is a very simple example. So what I'm going to do now is I'll go over another example where they don't equal 0 to show you it in more detail. And this example turns out to be very similar to your homework. Homework question 3. So actually this should be just 2.5, shouldn't it? I think. Slightly more realistic example. So we have let's solve this equation here. So the second derivative of y plus x squared plus 2 is equal to 0, and the boundary conditions are evaluate y at 0 gives 0, and evaluate y at 1 gives 1. So we'll use the 3 different weighted residual approaches to solve this equation. So this has an exact solution. So the exact solution, which we can use to check the answer. So the exact is sine x divided by sine 1 minus x squared. And you can check that by substituting this into the equation, the differential equation. Okay, so in order to solve this, we'll assume that there's two terms in the trial function. So again, let's use two terms in trial function. So then we'll have something like y as a function of x is equal to alpha 1 psi 1 x plus alpha 2 psi 2 x. Okay, so we can choose what our trial function is. But I'm going to suggest that we try having the same type of equation. So x squared minus x for the basis function 1 plus alpha 2 x to the 3 minus x. So let's try using the same form of the trial function. So we know that this is the real answer, but we're going to guess that it has this form. See how close we can get. Okay. So that's our trial function. So that's step 1. Is that right on our step 1? Trial function solution assumed. Step 2, satisfy the boundary conditions, and then and so on. So I'm going to go through those steps on the computer. So this trial function has to satisfy the two boundary conditions. So at y0, we can substitute in zeros, and we'll get 0. And then y1, we can substitute ones in, and is that going to give us a 1? That will give us a 0. That's not good, is it? Oh dear. Yeah, right. I think that's a mistake. That should be 0 there. It has to be, because that will be satisfied, right? You see that? Okay. Phew. Okay, so then the residual, if we substitute this is our trial function, and now with this choice, it satisfies the boundary conditions. So we've satisfied, that was step 2. So now step 3, let's substitute in the trial function into the differential equation. So we have the residual is going to be equal to the second derivative of r hat with respect to x squared plus y hat with respect to x squared, y hat plus x squared plus 2. So we ideally would like this to be 0 if it satisfies across the entire range from 0 to 1. We'd like this to be 0 from 0 to 1, because then the trial function would be exact. So now, but we know that the trial function is unlikely to be exact, so it would have some non-zero value. So we want this to go to 0, the residual. So we can evaluate it by substituting in the derivatives. So take the first derivative of y with respect to x, and so if we take the derivative of this, we're going to get alpha 1 2x minus 1 for the first term plus plus the second term, which is going to be 3, going to be alpha 2, 3x squared minus 1, like that. And then the second derivative is going to be 2 alpha 1 plus 6 alpha 2x. Okay, so then we substitute, so we've got the second derivative, now we can substitute into our residual equation, and we'll get out a function. So we have 2 alpha 1 plus 6x alpha 2 plus alpha 1 x squared minus x plus alpha 2 x3 minus x plus x squared plus 2. So this is just y hat here, right? And then we can collect terms. So we have alpha 1 2 minus x plus x squared plus alpha 2 5x plus x to the 3 plus x squared plus 2. Okay, so that's our residual. Now we've got our residual, and again we want to evaluate this equation across our whole problem domain. We want this to go to 0. We want to try to make this integral go to 0 across the whole problem domain, and that will minimize the error. That's the idea. So we've evaluated the residual equation R. Actually, I put a hat on there. There doesn't need to be a hat. And so we're going to choose W to be 3 different things. We're going to try A, we're going to try point collocation, and we'll choose x1 to be 0.25 and x2 to be 0.75. So we'll choose those 2 points to force the error to 0. And then we're also going to try the least squared method. So in the point collocation, the weighting function is equal to the delta function. In the least squared method, the weighting function is equal to the derivative of the derivative of the unknown terms, derivative of the residual with respect to the unknown terms. And then C, we're going to use the Galerkin method, where the residual for each term, let me write this out a bit more clearer, this point collocation. So the point collocation Wi is equal to delta x minus xi. And then the Galerkin method, the weighting terms, 2 weighting terms, are equal to the basis function. So psi I, where these are the basis functions, right? Basis. Okay, so let's see what we get, and I'm going to do this. I'm going to evaluate these 3 in MathCAD. Okay, so this is the example. So the first approach is the point collocation method, and I've written it out into steps. So this is the step 1, where we choose the trial function, and it satisfies the boundary conditions. And then this is the residual. I evaluated it taking the second derivative, and then so I write out the residual equation. And then step 4 is I need to satisfy with the point collocation the residual has to be 0 at the 2 points that we chose. So these are the 2 points, 0.25 and 0.75. So substitute those into the residual, and then we have 2 equations with 2 unknowns, alpha 1 and alpha 2. And then we can solve for those, and in MathCAD you can just write that out and solve it. And then I get out that alpha 1 is 915 divided by 899 to the minus, and then alpha 2 is 16 over 93. And so then so I've got my alpha 1 and alpha 2, and then I can substitute that back in, and then I've got my trial function solution. And then our exact solution is shown here. So then I can calculate the error, the percentage error across the problem domain. And so I did that here. I took the difference and calculate the percentage, and you can see that the error is pretty darn good. It's between it's a bit less than 0.4, plus or minus 0.4. It's really quite good. So that, and you know, it's not a sign term we have here. So that looks pretty good. This is a plot of the two, if you make a plot of them, and you can't really see much difference. So that would be a pretty good approximation. Okay, so that's option 1. Option 2 is we use the least squared approach. So again, this is the same. So we have the same trial function. I've recorded alpha 3 and alpha 4 in here. You can see this okay, can you? The alpha 4 and alpha 3, because I don't want MathCAD to get upset. So now we're going to solve for these 2 unknowns. And so then we've got the residual, and now the least squared method says that we need to take the derivative of the residual with respect to the unknown coefficients, so that they are alpha 3 and alpha 4. And so that gives us these two equations. So now we substitute the derivative of the residuals and multiply them into the integral equations, where we have the derivative of the residual times the residual, and then we integrate that from 0 to 1. And so we have two equations and 2 unknowns. The 2 unknowns are alpha 3 and alpha 4 in this case. And so we can solve, and then we get out different unknown terms. So here you can see this one is 64,111 divided by 62,973. So it is different. So we didn't get the same answer. And so then we can compare. And so here I've plotted the 2. And so the red is the point collocation, and the blue is the least squares. Interestingly, in this example, the point collocation, we just simply, it's the simplest one. You're just saying, let's make the error 0 at these 2 points. That gives a lower error than the least squared. So the least squared more complicated and not as accurate in this example. But if you look at the plot, they still, over here, still the error is very low. But another interesting point is, so that the point collocation, the error is both positive and negative. The least squared, the error is only positive, right? Because we're squaring it. And then lastly, the main point of all this is to show the Galerkin method. And so with the Glucan Method, we have the trial function, and now I've called them alpha 5 and alpha 6, 2 unknowns. And so we have the same trial function as the other 2. And now the difference is that we in the integral we have the residual, which is the same as in the other 2 cases, but we make the weighting function equal to the basis function. So that as I've said, the basis function is the part in front of the trial function. So in this case it's x squared minus x and x to the 3 minus x. So that goes in the integrals. And then so we integrate these two and we get out again two equations with two unknowns. And then we solve. And then I did that. So we get 7 over 41 and 377 over 369. And then I plot them, and then so we've got the Galerkin method here coming in lower. But we can also look at the this is just the product of the error, and you can see that the Galerkin is in the blue. This is just the difference, not the percentage. But you can clearly see the Galerkin comes in at having the lowest error, and that's often the case, and so that's why the Galerkin method is the one that's primarily used in the finite element method. So that's the one we're going to use. So I needed to explain this, because otherwise when I talk about the finite element method and say, well, we're choosing the weighting function to be equal to the basis function, if you didn't discuss this first, then you wouldn't know what that meant.